The built environment demands a staggering amount of resources to construct and maintain. It accounts for 2/5 of the world's material and energy flows. The ongoing operational cost is where the most severe draw occurs. Buildings consume 60% of all electricity generated worldwide. In the developed world, that demand is even heavier. Structures in these regions pull more than 70% of the total electrical load. The primary engineering discipline responsible for managing this immense draw is heating, ventilating, and air conditioning, or HVAC. The first baseline function of an HVAC system is generating and maintaining specific environmental metrics, like temperature, humidity, and air motion, to keep human occupants comfortable. The second baseline function operates under much stricter parameters. These systems must supply extreme environmental conditions required for industrial processes. A textile mill, for example, requires high temperature and high humidity to operate effectively, while grain storage demands precise, continuous low temperatures to prevent spoilage. Balancing these diverse parameters requires complex systems engineering. The efficiency of the equipment chosen directly dictates the energy viability of the modern world. To engineer an energy-efficient building, we first audit end-use profiles to target the highest yield opportunities for savings. This chart shows the breakdown of average energy use in U.S. commercial buildings. Space heating commands the largest share of the load, consuming 25% of the total energy budget. Add in the secondary mechanical requirements, ventilation at 10%, space cooling at 9%, and water heating at 7%, and thermal management clearly dominates the building's electrical draw. Moving the dataset to the European Union commercial sector proves this is a consistent engineering reality across the globe. In Europe, the dominance of space heating is even more severe, consuming an overwhelming 52% of all commercial energy. This pattern holds true in residential structures as well. Heating represents 44% of home energy use in the US and a massive 67% in the EU. Converting source electricity into these thermal end uses inherently produces waste. Every conversion process involves a degradation of energy, meaning a portion of the raw fuel is lost before it ever heats or cools a room. Because thermal loads dominate budgets across both commercial and residential sectors, optimizing heating and cooling is the most mathematically effective way to curb global energy waste. We also have to account for the external source supplying the building's power, the traditional electrical grid. The current grid relies heavily on large-scale thermal generation, operating centralized fossil fuel, nuclear, or geothermal stations located miles from the end consumers. These thermal plants are highly inefficient at the source, operating at only 30 to 40% efficiency. The majority of the raw energy is immediately lost to the atmosphere as waste heat. As the surviving electricity travels across vast distances to reach cities, it incurs an additional 5% loss in the transmission lines. This infrastructure was built strictly for a one-way flow of electricity, pushing power from the utility downstream to the customer. Operational communication stops entirely at the utility meter. The grid operates without any real-time data on how the customer's HVAC system is actually performing. The utility network only communicates with the building during a contingency, like a total power outage. By the time electricity reaches the outlet, roughly 2/3 of its original energy has already been wasted. If a building runs an oversized chiller or a poorly selected boiler, that mechanical inefficiency forces a massive overconsumption of raw global resources upstream. To mitigate this grid inefficiency, engineers build inherent thermal control directly into the architecture of the structure itself. The physical shape of a building, whether it is L-shaped, A-shaped, or rectangular, dictates where heavy equipment can be located and how ductwork and piping are routed. Even with the same square footage, the aspect ratio of the floor plan drastically alters the required mechanical refrigeration load. A rectangular building with a 4:1 aspect ratio has a much longer boundary line, exposing significantly more perimeter area to the weather than a square building. That perimeter exposure is amplified by the building's geographic orientation and its fenestration, the amount of light-transmitting glass used in the walls. When glass covers a large portion of the exterior, the perimeter load alone can dictate 30 to 60% of the entire air conditioning requirement. To regulate these factors, ASHRAE Standards 90.1 and 100 enforce efficiency by defining an annual building energy budget, calculated in total BTUs per square foot. Instead of relying strictly on prescriptive rules for building materials, These standards provide flexible system performance goals. Engineers can combine innovative materials and systems as long as the total design meets the annual energy budget. A structure with optimized orientation and minimized perimeter exposure requires smaller HVAC equipment, keeping capital costs low and directly reducing operational carbon emissions. The global population is projected to reach 9.7 billion by 2050. To accommodate that urbanization, the world will construct a new city the size of Singapore every month for the next 2.5 decades. The traditional one-way power grid cannot handle this density. This is especially true as intermittent renewable sources like wind and solar replace baseline thermal generation. Add the projection that 33% of all vehicles will be electric by 2040, and the grid faces unpredictable, massive spikes in demand. The engineering solution relies on direct digital control, integrated into complete building automation systems. Instead of running blindly on a static schedule, a building automation system uses real-time data to optimize internal mechanical loads, like adjusting variable air volume systems to match exact room occupancy at any given minute. Modern certification standards, including LEED and the EPA's Energy Star program, now mandate this level of integrated automated design. To earn an Energy Star label, a structure must perform in the top 25% of similar buildings nationwide. Hitting that metric is nearly impossible without treating the building as an active, responsive data node. The objective of modern HVAC engineering extends past basic indoor climate control. Engineers now orchestrate dynamic, sustainable ecosystems designed to protect the future viability of the global power grid.